All right, this video is on conjugate acid-base pairs and how to identify who's a conjugate acid and who's a conjugate base. So, let's talk about just a generic reaction. So I'm gonna do HX with water. Excuse me. And I'm gonna make this a reversible reaction. And so we're going to treat HX like the acid, and water is going to be the base then. So the acid is going to donate its hydrogen to water. So I'm going to be left with X minus, and then H3O plus, right? Because H2O with an H plus would make it H3O and a positive charge, and it's going to be aqueous. Okay, so we've already identified the acid and the base. Now, what has to happen is that these come in pairs, okay? And so we have a conjugate base and a conjugate acid. So let me define this first. So an acid-base pair that differs only in, let's see, how can I say this, the presence or the absence of an H plus or a proton are called a conjugate acid-base pair. So every acid has a conjugate base, and every base has a conjugate acid. So I'm going to write that. So every acid has a conjugate base, and every base has a conjugate acid. All right, so what we're looking for is we're looking for this chemical species who differs by just either the addition or the loss of an H plus. But then we're looking for the behavior aspect. So let's talk about the acid. Okay, so we know that an acid is one who can donate the hydrogen. So what we're looking for is its conjugate base over here, okay, who then would be able to accept the hydrogen if it was going the other direction. And so that would be the X minus. Okay, so in this case, this is a pair. So this is referred to as the conjugate base because see, X minus can accept a proton and turn itself into HX. So then my other pair would be the base with the conjugate acid. And so remember, the base is the one who can accept the H plus, and so a conjugate acid would be the one who has an H plus to donate. Okay, and if you look at these, so we have HX and X minus, right, as one acid and then conjugate base, and then we have H2O as the base and H3O plus as the conjugate acid. And notice that in this pair, the only difference between them is an H plus, and in this pair, the only difference between them is an H plus. So that will always be the case with a conjugate acid-base pair. Okay, so the way to,
Allison Harmon, please report to the main office. Allison Harmon to the main office.
The way to get kind of good at this is to practice writing the formulas for conjugate bases and conjugate acids, and then we'll do a couple of reactions where we write them out and then like categorize or identify who's the acid base, conjugate base. Okay, so in this first one, and always you're welcome to pause this and try it without me, or you can just listen to my explanation. So in this first practice, it says, what is the conjugate base of each of the following acids? Okay, so these are the acids listed, and we want to know the conjugate base, which is going to be the one who has lost the proton so that then it could turn around and regain the proton. So the trickiest thing about this is getting the charge correctly. So in this case, to take away that proton, I'd be left with ClO4, and this thing was neutral, right? And I'm taking away a positive, which means this is going to be negative. You can always think about it. You can always check yourself by like going backwards and then saying, okay, well, if I were to add an H plus to this, minus 1 plus 1 would give me a neutral compound. Okay, so it's a good idea if you're worried that your charge is incorrect. Oop, that was right. If you're worried your charge is incorrect, that you can check by adding the proton back. In this case, the conjugate base would be one less hydrogen, so it just HS, and again, it's going to be a minus. Adding that H plus back in would give me a positive. Would give me a neutral compound. In this case, I'm going to take away an H plus, which is going to leave me with PH3. And then this time, when I remove that positive, it's going to be neutral. Again, you can check yourself by saying, if I added this, it'd be PH4 plus. And then in my last example, HCO3 minus. If I'm going to take away the hydrogen, it'd be CO3. And this time, I'm taking away a positive, so this is going to be a -2. And again, check yourself. If I add the H plus back, -2 and +1 would give me -1. So when in doubt of your charges, because that can be a little tricky sometimes for students, you can always check. In the second example, what is the conjugate acid for each of the following bases? So in this case, you're going to create the conjugate acid by giving it the hydrogen, right, which then in fact it could turn around and lose to act like it, or to donate to act like an acid. So in this case, I'm going to add, I'm going to add the H plus back in, and so this would be HCN. Again, you can check yourself. This way I would go up here and say if I added the H plus, it'd be neutral. Adding an H plus to HSO4 minus is going to give me H2SO4. Okay. Adding an H plus to water, we should be familiar with because we've seen this. This is the hydronium ion. And adding an H plus to HCO3 minus is going to give me H2CO3. So those are your conjugate acids. Remember that a conjugate acid can then turn around and behave like an acid by donating its proton. A conjugate base can act like a base by accepting a proton. And they always come in pairs. So here's where we're going to write a reaction in practice. So it says the hydrogen sulfate ion, who is HSO3 minus, is amphiprotic. Write an equation for the reaction of this ion with water in which it acts as an acid and identify conjugate acid-base pairs. Okay, so HSO3 minus plus water. So this is going to be the acid, it's telling me, which means this is going to be the base. Okay, the acid's going to donate its proton to the water, so I'm going to be left with SO3 minus 2, and then H3O plus. And so this is a pair, right? And then this is a pair. So if this is the acid, then SO3 minus 2 is the conjugate base. And water is the base, and so H3O plus is the conjugate acid. And B, write an equation where this same ion, HSO3 minus, reacts with water but behaves like a base. So this time this is going to be the base, and this is going to be the acid. So if water's the acid, I always think about it from the acid perspective. I just think it's easier. So water is going to donate its hydrogen, so I'm going to be left with OH minus. And then putting the hydrogen plus on this would give me H2SO3. So here's a pair. Here's a pair. Remember, I can identify them very quickly because they only differ by an H plus. So if this is the base, then its pair is the conjugate acid. And if this is the acid, then its pair is conjugate base. And then the very last thing, this is old discussion, but we have to talk about what it means to be a strong versus a weak acid and base. So for our strong acids and bases, you'll recall that this means 100% ionization. Okay, the acids, there are 7, HCl, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. And we'll be talking about this in more detail later, but just for a quick review. And then your strong bases are all group 1 hydroxides. So anything in group 1 with OH. And then your heavy group 2 hydroxide. And that would be calcium, strontium, and barium. Your weak mean partial, very small. Your acids are anything left. So some famous examples, HF, acetic acid. And then your bases, we're going to do a discussion of weak bases, but probably the most famous is the one we have just been talking about, which is ammonia. Okay, so we're going to see why it's a weak base later, but for now, that's just a really, really quick review of what it means to be a strong versus weak acid or base. Okay, so that's a discussion on how acids and bases work together to generate what we call a conjugate acid and a conjugate base. They differ by only a hydrogen ion or a proton, so you should be able to, at this point, identify who's the acid, who's the base, who's conjugate acid, who's conjugate base, and then just a very quick discussion on strong versus weak acids and bases.